This video is on conservation of energy. Remember from our previous units on momentum and last year in chemistry, when something is conserved, that means it stays constant. So remember from last week that work is what causes a changed energy. Keyword change. So we can either change the kinetic energy, or we can change the potential energy by doing work on an object. If there's no work done on an object, then that means that the energy is not going to change. Specifically, the total energy is going to be constant. When something's constant, we say that it is conserved. So, for example, suppose you have a pendulum that swings back and forth. Like you pull it up, and then you let it go, and we look at it at three different places as it swings back and forth. If the pendulum starts with 0 joules of kinetic energy, like you're just holding it, and 10 joules of potential energy, then its total energy is 10 joules. As the pendulum swings back and forth, no work is being done on it, so the total energy is always going to be the same. We say that it's being conserved. So since it started with 10 joules of total energy, it's always going to have 10 joules of total energy. What this lets us do is figure out what the other forms of energy are at any of those given spots. So at the bottom, if I know the potential is 0, then I can say that the kinetic energy is 10 joules. Same thing over here. Let's suppose where the pendulum is blue, I know that the kinetic energy is 4 joules. I may ask you, what is the potential energy? The total still has to be 10. So just subtract 4 joules from 10 joules to get the potential energy, which would be 6 joules. When you appear to lose energy, it's going to one of 3 forms. Most of it's going to heat, making the object hot. You can verify this by doing work and rubbing your hands together. Your hands are going to get hot. The second would be sound. You can hear your hands rubbing each other. And the third form that we really don't see very often, but it is possible, is for energy to be lost to light. A good example of that is a light bulb. Electrical energy is being lost to light inside of a light bulb. Another way to put the conservation law is to say that energy is never created or destroyed. Let's take as an example the question on page 11 dealing with a skateboarder on top of a U-shaped ramp. So this is question number 3. It asks you to describe how his energy is transformed as he rides down the ramp and up the side, and draw a graph showing the energy distribution. So here's kind of a picture of what it looks like as he's going down the ramp. Start out at the top, goes down towards the bottom. As he's going down, his height's going down, so his potential energy decreases. So UG goes down. Since there's nothing doing work on him, the energy is conserved. That means the kinetic energy has to increase. And if you've ever done something like this, you know as you go down the hill, you go faster and faster. So if we graph the potential energy, kinetic energy, and the total energy, G versus time, we'd do something like that. Kinetic would go up, potential would go down. The total has to be constant. It's going to stay the same. So on the graph, it would just make like a flat line. As he goes up the other side, his height is increasing, so his potential energy has to increase. Where's the potential energy coming from? It's coming from the kinetic energy. So the kinetic energy goes down, potential energy goes up, but the total still stays the same. So in the graph, you would see the potential energy go back up, the kinetic energy come back down, but the total is always a flat line. It doesn't change. Another way that we could represent the energy transformation is by drawing pie charts. So I've got like a pie chart for each of those 3 positions. At the top and bottom, he's got all potential energy. So I'm going to make that orange color be like potential energy. The bottom, he's got all kinetic energy. That's the pink color. Somewhere in between, you would have a little bit of both. Have some potential, some kinetic. And the higher up he gets, the more the pie chart would be orange, and the less would be pink. Let's look at a little bit more complicated example. This one's from page 12, and it's basically the only problem on the page because there's a lot that it's asking you to do. You've got a pendulum, and you pull it back to point A, and it's going to swing back and forth, and there's a table on the page that gives you some information and wants you to fill in the missing parts. So in the first point, point A, it tells you that your velocity is 0 and your total energy is 36 joules. Since your velocity is 0, that means your kinetic energy is 0. If your kinetic energy is 0, then that 36 joules must all be potential energy. So the last thing it wants you to do is figure out the height. So you just solve your potential energy equation for height. Your mass of your pendulum is 2 kilograms. That's given to you. And when you do that, you would get 1.8 meters. This pendulum starts at a height of 1.8 meters. At point B, you're told that the velocity is 2 meters per second, and you've got to find all the rest of the things. The thing that you need to remember is that your total energy stays the same. So your total energy is 36 joules. Since we know that the velocity is 2 meters per second, we can figure out what the kinetic energy is using our 1/2 mv squared equation.
You may copy anything while I'm going.
So if we know the kinetic energy is 4 joules, we can just subtract from the total to get the potential energy. So I know the potential energy is 32 joules. Do the same thing we just did a second ago, figure out what the height is. Solve the potential energy equation, and we would get a height of 1.6 meters. Point C, we still know that the total energy is 36 joules. Now we're told that the height is 0, which means potential energy is 0. So that 36 joules must all be kinetic energy. So I'm asked to find the velocity, so all I have to do is solve that equation for the velocity, square root of 2k over m, and we would get 6 meters per second for the velocity. Point D, energy is still 36 joules. That's never going to change. You're told the potential energy is 11 joules. So a couple things we need to figure out. First, the height. We've already done that 2 other times. Second, we need to figure out what the kinetic energy is. Since I know that the total is 36 joules and I know the potential is 11, just subtract to figure out what part of it is kinetic. You get 25 joules. Again, find the velocity, square root of 2k over m, and the velocity comes out to be 5 meters per second. The last point, point E, your energy is still 36 joules. That's the thing that stays constant. That's the big idea you need to know. You're told the kinetic energy is 9 joules, so first thing you can do is find the velocity, which is 3 meters per second. Same thing we just did. Your potential energy would be 36 joules minus 9 joules. Whatever's left over has to be potential energy. And then we can find the height. We've done that several times here, and you get 1.35 meters. Now the big important thing you need to remember is that the total energy is constant. That 36 joules, that came from your brain each time because you know that the energy stays the same. The last question we're going to look at is on page 13, question number 2. You're given a roller coaster, and you're given its mass and the height it starts at, and you're told its velocity at its starting point is 10 meters per second. Part A just says find the total mechanical energy of the roller coaster. That just means add up the kinetic and the potential. So find the kinetic energy. You would get 1,000 joules. Find the potential energy. That would give you 12,000 joules. And then the total just means add them up. That would give you 13,000 joules. Part B says find the velocity of the roller coaster at point B, which is 20 meters above the ground. That means that your total energy is still 13,000. I can find the potential energy at that point. It gives me a new height, and so my new potential energy is 4,000 joules. Since the total has to stay 13,000 joules, just subtract the 4,000 joules of potential energy to get your new kinetic energy. So I'll give you 9,000 joules. Solve your kinetic energy equation for the velocity, and you'll get a velocity of 30 meters per second. Part C, says figure out the velocity of the roller coaster at point C, which is on the ground. Well, the ground means that the height is 0. That means the potential energy is 0. Energy is still conserved, so the total is still 13,000. That tells you your kinetic is 13,000 joules. Do the same thing. Figure out your velocity from your kinetic energy, and at that point it would be 36 meters per second. Part D says figure out the height of the second hill H, where the roller coaster has a velocity of 18 meters per second. So it gives you the velocity. You can figure out the kinetic energy. That gives you 3,240 joules. Total still 13,000 joules. That's the magic number. So that lets me figure out the potential energy. Just subtract the 3,240 from the 13,000. And then figure out your height from your potential energy. You get 48.8 meters. You can round that to 49 meters. The last part says figure out how much work is needed to stop it. When you're stopping the roller coaster, you're just changing its kinetic energy. It's not changing heights as you stop it. So all you have to do is work equals change in energy. Your final kinetic energy is going to be 0. Your initial is that 3240 we just found up there a second ago. So that means your work is just negative 3240 joules.